All right, we're back, and now we're going to move to the other attribute substitution that I wanted to talk about in this chapter, which is representativeness heuristic. So remember, heuristics are efficient strategies that usually lead to the correct answer. As is the case with most things in cognitive psychology, the easiest way to understand how people actually think is to look at the errors that they make, right? So when we see that people are thinking that rare things are more common just because it's something that they easily think of, in the case of like the availability heuristic, it shows us what they're focusing on and what rules they're using to try and decide what to put their attention on. Same thing with the representativeness heuristic. We understand this principle because of the errors that it causes. So the representativeness heuristic tells us that if an event matches your prototype, it's probably a member of the category. So if an event matches your prototype, if it represents your prototype for a category, it's probably a member of the category. That seems like a safe bet, doesn't it? It seems like a safe judgment to make. It matches my prototype for a category, it probably belongs to the category. Why does it look so close to my prototype otherwise? So let's give some examples. All right, so let's look at this fellow. All right. If I told you that this fellow likes to read and he lives in a college town, all right. Hopefully you're thinking some thoughts about him. Now, if I ask you, is he a rock climber or is he a rock climber and a professor? Which would you say? So I know for me, he sure looks like a professor. He likes to read and he lives in a college town. Seems like all pieces of information are pointing to him representing my prototype of a professor. He actually just physically and liking to read makes me think English professor. I'm even going to get more specific and I'm going to say he's probably in the humanities, right? He's probably English, maybe philosophy. So he's not only fitting my prototype of professor, but he's fitting my prototype of a specific type of professor, right? I guess he could be a rock climber too. I guess so. I mean, professors do different things with their free time. I guess he could be a rock climber too. But I can tell you, he certainly matches my heuristic, my prototype for a college professor. So I'm going to go ahead and I'm going to say I think he's a rock climber and a professor because I know he certainly looks like. I have nothing else to go on. All I have is what he looks like, and then these two pieces of information. He fits my prototype of a professor. I guess he could be a rock climber too. So let's say that this is the whole world of people who are professors. By the way, this Venn diagram is not drawn to scale. So we've got a professor. And then we've got the whole world of people who are rock climbers. And we have this little overlap right here where you have people who are rock climbers and professors. The base rate of rock climbing professors is going to be by definition low, right? This is the little sliver where we have this overlap. The base rate means the number of that kind of people in the population. The likelihood that you would come across a person like that is really small. Overlapping. Your best bet is to say that he is one thing, even if it's not the thing that he most closely represents. He doesn't look to me like a rock climber. I mean, a lot of rock climbers do live in college towns. A lot of rock climbers like to read. So those two things, that could go either way, honestly. But the way he looks, I'm like, well, he doesn't look like a rock climber. But I still would be safer, even though he doesn't really represent my prototype of just strictly a rock climber. I would be safer if I went just rock climber because it's much more likely that he would be one thing than he would be in this little area of overlap between two things. So sometimes the representativeness heuristic causes us to make judgments that are inaccurate for an individual, right? It'll cause us to violate the base rate data. Like we don't even take it into consideration that the two things are less likely than one thing. We don't even think about that. When in fact, of course, two things is going to be less likely than one thing. But I feel so confident that he looks like a professor, I'm willing to take that risk, that he's a professor and a rock climber. And that's what the representativeness heuristic does to us. It tells us, I know it's unlikely numerically, but it doesn't really matter because I'm sorry, he looks like a professor. What it is, he looks like a professor. I'm going to say that. And so we oftentimes will make the wrong judgment, at least statistically. Now, why do we do it? Well, because we're right a lot of the time. We're so often right that he is a professor, and I guess he rock climbs too. He's one of those few people that falls in the overlap. So, but what I want to really underscore is that all you know is what he looks like, and then those two little pieces of information. He likes to read, and he lives in a college town. When you have so little information, you're actually better off saying he's the one thing. You're more likely to be right if he's the wrong, by saying that he's just the one thing. But we tend to violate that base rate information when we have an example that matches our prototype so well. So what we're kind of getting at is something called the base rate fallacy. This is our tendency to fail to take the frequency of the event into account, right? We don't really process that statistical information when we're making judgments. A lot of times we forget to do that. Our textbook goes into some circumstances that can cause us to focus on the base rate accurately, but the one thing that you should take away from it is that we'll focus on the base rate when it's put in front of us as the only piece of information. If we have other pieces of information, such as the individual matches our prototype, we will ignore the base rate. So that's what we call the base rate fallacy. So I'm going to apply this to an example that is kind of sometimes daunting to people because it has numbers in it. But stick with me. I think I'll be able to get you to understand what we're talking about. So let's say that there is a disease out there where the prevalence is that 1 in 1,000 people have this illness, whatever this disease is. Okay, so you have a 1 in 1,000 chance of coming across an individual. So for every 1,000 people who you test, one of them is going to actually have the disease. So let's say that we have a test for this disease that 1 in 1,000 people have. And let's say that that test has a false positive rate of 5%. So false positive means that the test mistakenly indicates that the disease is present when it really isn't. So it has a 5% chance of telling you that you have the disease when you really don't. So 5% false positive rate. Okay, so that means 5 people in 100 will be told that they have the disease when they really don't. That's what 5% means, right? So five out of 100 people who take the test will be told that they have the disease when they don't. And the disease occurs in 1 out of 1,000 people in the population. So let's say that you have an individual before you who has tested positive for this disease. What are the chances that that person who has just tested positive for the disease actually has the disease? Assuming that you know nothing else about the person. All you know is that there's a 1 in 1,000 prevalence rate. So 1 in 1,000 people have it. The test that you just administered has a 5% false positive rate. So 5 people out of 100 will be told that they have it when they really don't. So 5% false positive. Now I'm going to put it into 1,000s just to make it consistent with the prevalence rate. So 5% false positive, that's 5 out of 100 or 50 out of 1,000. So 50 out of 1,000 healthy people who don't have the disease, will test positive for the disease. So let's say basically 51 people should test positive out of 1,000, right? Like 50 will be told that they have it when they really don't. And one person who really has it will test positive in 1,000 people. So that means that 1 out of 51 actually has it. That's going to produce about 2% chance that a person who tests positive actually has the disease. If you divide 1 by 51, it's roughly 2%. It comes out to roughly 2%. So if you have a person before you who has tested positive for the disease, they feel like, oh God, I have it. Oh no, I have the disease, whatever this is that this is testing for. But the truth is they have a 2% chance of actually having the disease given the prevalence rate of 1 in 1,000 and a false positive rate of 5%. A false positive rate of 5% is pretty low, actually, for tests. when I was having my first baby, they wanted to administer a test for, it's called AFP, and it tests for the presence of spina bifida, which is a disease that attacks it prevents the spinal cord and the spinal column from developing correctly. So you can end up with paralysis and some other things. And so they wanted to administer this test. And I said, well, of course, I'm a PhD in psychology. So I'm like, so what is the, false positive rate on this test that you want to administer? And they told me 30%. 30%. No, thank you on that test. I'm too neurotic to potentially get a positive result and then have to wait several weeks before we can do a follow-up, more specific test to find out. I'm like, nope. I do not need that test. I will freak out for the next 5 weeks while I'm waiting to see what else, no, thank you. I didn't even see what the point would be that, I had a really good chance of being told that I had tested positive and I wasn't. My baby wasn't. So I didn't do it. Now, here's something I want to put into context in current events. We have tests for COVID that have the rate of false positives has never concretely been determined because the prevalence rate has never been concretely determined. And so we have these tests that may or may not be, they may be returning positive results for people who are not positive. But we don't know what the rate of that is. So we have no way of judging the accuracy of those tests. So that's something to keep in mind. I mean, it's one of those things that can fuel incorrect thinking, right? If we don't know what the base rate of something is, prevalence is another word for base rate. So what is the base rate of this illness in the population? What's the risk of a false positive on this test? What's the likelihood that I actually have the illness that this test is testing me for? Those are things that we have to keep in mind. And it's hard to make these judgments unless we know these numbers. And if you do know the numbers, you have to be able to, sort of calculate it out to figure out, okay, if I test positive, do I actually have a 2% chance of actually having the illness, right? We need to know what those rates are. All right. This next section gets at how we detect covariation. We call them illusions of covariation because, again, what we're most interested in oftentimes in research is the times that we make mistakes. That gives us a lot of insight into how people make judgments, right? And so when people make mistakes, we realize what they're basing their judgments on. You may have heard of this before, like when I teach this in Psych 209 or 309, I call this illusory correlation. So you may have heard it called an illusory correlation in the past. Here's a cartoon from the family circus and the kid's flying and he says to his mom, I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy. He's thinking, that the seatbelt sign and the bumpiness are somehow co-varying in a causal way, right? Where he thinks that the seatbelt sign is causing the bumps, whereas we all know the bumps are causing the seatbelt sign. So these illusions of covariation are what we're going to talk about next. So there are a lot of superstitions that are based on illusions of covariation. Here's an example. If you talk to any nurses, they will very adamantly state that there are more hospital admissions, there are more babies born, there are more psych evaluations, all these kinds of things on full moons. And so I wanted to kind of talk about that superstitious belief. So we've got hospital admission, no hospital admission. We've got full moon, no full moon. And then we have all the intersections of those things. So if it's a full moon and it's a busy night for the hospital, that attracts attention because it's consistent with the belief. And so it's easy to see that and then to say it's happening because of the full moon. We're seeing all of these hospital admissions because of the full moon. And so we explain it away like that. What we tend to ignore is the fact that on nights where there are no full moons, which is let's say the other 20 6 days of the month, right? Um, Something just hopped on my screen, so I'm sorry for that pause. So the other 26 days of the month, I'll bet some of those were busy too, but they're not as noticeable because there wasn't a full moon and it's not consistent with our existing belief that these things go together, that one's causing the other. We have nights on the full moon that are slow. Sometimes full moons have slow nights where nothing's going on at the hospital. And I'm sure there are certain explanations that people will give. Oh, well, that was Super Bowl Sunday, so nobody ever goes to the hospital on Super Bowl Sunday, or something like that to explain away why we're not seeing the behavior that you told me always happens on a full moon, right? And then we have this final quadrant, which is no full moon, no hospital admission. Nobody's paying attention to that, right? Then nobody's interested in that data. What attracts people's attention is the time that the behavior is consistent with the superstition. That's what attracts people's attention. And that's how illusory correlations form. That's how illusions of covariation occur. Stereotyping is the most common example of illusory correlation. Making the assumption that a person who looks like this also has these characteristics, or a person who has this sex, male or female, also has these characteristics. A person who believes this must always also have these characters. That what we're saying is these things go together. And maybe we only need one little cue, appearance or belief or something like that. And then we invoke in our minds all the other things that we assume go with it. And that's stereotyping. So at the heart of it, stereotyping has roots in illusions of covariation, this belief that things go together that don't necessarily always go together. You can look any way and believe that set of beliefs. These things don't necessarily go together, but we stereotype people and assume that they do. A lot of this is driven by confirmation bias. I know during the pandemic, everybody learned the term confirmation bias. It suddenly was like on all the memes and everything. Everybody knows this now. But the official definition, in case you weren't one of the people who watched enough TikTok during the pandemic, it's the tendency to be more alert to evidence that confirms one's belief than to evidence that challenges it, right? So confirmation bias, we seek out information that confirms what we believe. And I would like to argue even more strongly than this definition that comes from our textbook. I would like to say something stronger than that. It's not just that we seek out information that confirms our beliefs and then we don't pay as much attention to information that challenges them. We plug our ears and say, la, 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 I can't hear you, to information that challenges our beliefs. We don't want to hear it. Particularly anything that we really actually strongly hold, any belief that we actually strongly hold. High probability that we are actively trying to avoid information that would challenge what we believe. So that's the confirmation bias. And so I'm going to go ahead and stop here, and we'll come back and we'll address the confirmation bias through the lens of a dual process model in the next video.